said, hey, you, let's do some DiffEQ. If something's looking blurry, then we'll bring it into view. I said, hey, you.
Check it out.
Welcome. Let's do some DiffEQ. In this video, we'll review concepts related to the Laplace transform. Let's get started. The definition of the Laplace transform is that it's an integral as follows here. If we have a function that's defined on the non-negative real numbers and it outputs real values, the Laplace transform of that function is equal to this integral here. Where what we're doing is we're taking a function of, let's say, t to begin with, and in the end, since we're integrating with respect to t, we'll end with a function in terms of s. As we've seen, we move from functions of t to functions of s and then back. Now that is simply to say that we have this. At the same time, when we actually compute using this integral, we'll want to make note that s is going to be a constant as we integrate, since we're integrating with respect to t. S is treated as a constant. And in particular, we'll treat s as being positive, which will have an impact on the computation of limits. Let's go ahead and do a direct computation using this integral definition. Say we have the function f of t is equal to t squared, and we want to take the Laplace transform of that. That means we're taking the Laplace transform of t squared, giving us this integral. We take t squared and multiply it by e to the negative st, where we think of s as positive. If we do this integration, or find the antiderivative, and in particular, we do integration by parts 2 times. Once, because it's squared, and then twice again after that. We end up with this expression, and we're evaluating this expression from t is equal to 0 up to infinity. Now, we can't just quote-unquote plug in infinity, because infinity is not a real number. It's just a concept. It's not a real number that exists. So what we do is we make a substitution. We say we're going to take the limit as, say, omega goes towards infinity, and that will take to be a version of substituting in infinity. So we replace the limit of infinity here, the limit of integration, that is, or valuation limit, with this omega and limit as omega goes to infinity. Just quote-unquote plugging in infinity would be wrong and not make any sense. Now let's move this work a little bit just to free up some space. Using the fundamental theorem of calculus, we can substitute in omega, which now we take to be a real number that just gets larger and larger, but a real number. And then t is equal to 0. That gives us this expression here. Now we're going to take the limit as omega goes towards infinity, and we're going to make note of the fact that s is greater than 0. It's positive, which will have an impact on what this does in the limit. If we do that, we'll notice that since s is positive and omega is going to be eventually positive and stay positive thereafter, we have e to a negative number that gets larger and larger and larger, more and more negative. That means that this value is going to go to 0, taking all this to 0. And it should be said, yes, it's true, this also goes towards infinity, but exponential values increase at such a faster rate that they overpower just linear or quadratic or any polynomial increase. Said again, exponential increases vastly outpace polynomial increases. So this will win out, and this will go to 0 so much faster than this will go to infinity. This ultimately ends up being 0, leaving us with just this one term. So there was one computation, but you can do many others, and doing these computations is what gives us the entries in the Laplace table. It just happens to be that over time people have done those and assembled all the results into the Laplace table that we then use. But it's still useful to go back and make sure you can do this computation. Now let's look at the Laplace cycle that we use to solve differential equations using Laplace. So the way I like to describe it is as this cycle where we go from a t space, let's say in cyan here, to a s space in yellow. We start with a differential equation. let's say L of x is equal to f of t, where L meaning it's a linear differential operator, meaning it's a linear differential equation that's constant coefficient. We apply the Laplace transform, which, as we just saw, is taking this integral here. In doing that, what we end up with is some function of s. So we've converted from a function of, let's say, t to some function of s. We then algebraically manipulate to get a different expression in terms of s. Then we take the inverse Laplace transform, and we end up with a g of t. Where, said another way, we can think of it like this, where we get Laplace of x is equal to some f of s. We can rewrite it, and then we take the inverse Laplace transform, and we get that x is equal to g of t. So we were able to take a differential equation and find its solution. Now let's look at taking inverse Laplace transform. The presence of an exponential, either before or after taking the inverse Laplace transform or Laplace transform, works out in the following way. If you start with an exponential times, let's say, a cosine, that has the effect of taking the regular Laplace transform and shifting it by an amount equivalent to this value. Likewise, going backwards, if we have the Laplace transform of something, but we notice there's just a shift in it, that means that there was an exponential here multiplied by that function. On the other hand, if instead of having the exponential in the t space, if we have it in the s space, so we have it in the s space times some Laplace transform, for instance, this is just like 6 over s to the fourth, but it's just multiplied by this e to the negative 8s. When we take the inverse Laplace transform, what we get is essentially what we would have had, which this thing, if you take the inverse Laplace transform, goes to just t cubed. But now instead of t cubed, we do the shift over here. And also to account for that, or to go along with it, we have the Heaviside function. So notice there's a notion of shifting. If you're shifted in the s space, that's going to be represented by an exponential in the t space. If you have an exponential in the s space, that's going to be represented by shifting in the t space. So on one side there's shifting, and on the other side there's the exponential. So shifting here, s space, exponential. Here, the exponential. Here's the shifting. These are two that it can be easy to get hung up on, so just wanted to point these out. Now let's go ahead and actually just solve a differential equation through the whole cycle and see how it goes. Say we have this initial value problem. If we go ahead and apply the Laplace transform to both sides of this, what we get is this here. Now I've spaced out the differential equation just to make it easier to line up with the Laplace transforms. If we take Laplace transform of 17y, because of the linearity of the Laplace transform, that's the same as 17 Laplace of y. If we take negative 8 times y prime and then the Laplace transform, by the linearity, we can factor out the negative 8. And then the Laplace transform of a derivative is equal to this here, where I've highlighted the fact that we're taking negative y naught, which will ultimately be 2 in a bit. And then taking the Laplace transform of the second derivative, we get this expression, where notice now we have y of 0 and y prime of 0, which again I've colored to make it a little easier to track. Doing some substitutions of the actual initial value information, we get this here. Now combine like terms. Everything with a Laplace of y, combine that. Everything else, kind of shift that over. And we get this here. Do a little bit of algebra, and we end up with this. Now, a little more algebra, and we are here. Now at this point, all we have to do is take the inverse Laplace transform of both sides, and that will give us that y is equal to, whatever the inverse Laplace transform of this is. So now we just have to manipulate this right-hand side so that we get something that we can easily take the Laplace transform of. So we've applied Laplace transform to get to this point. Now we algebraically manipulate and then we will do the inverse Laplace transform. Let's look at how we might manipulate this algebraically. First thing we'll note is that this has strictly complex roots. That is, roots with a imaginary and real part being non-zero. In cases like this, what we want to do is complete the square. So in order to do that, we take 1/2 of this value, -8, take 1/2 of that, and square it. Then we'll add and subtract that, which is, of course, adding 0. So we get this, s squared minus 8s plus 16 plus 1. Notice we've just partitioned 17 into 16 plus 1. The reason we've done that is so now that we can take these first 3 here, and we can rewrite that as s minus 4 squared. So we took s squared minus 8s plus 16 and we rewrote it like this. That's just completing the square. If we just focused on the denominator, that's just an algebraic thing called, again, completing the square. From there, what we do is we notice that up top, we're trying to get an s minus 4 shift because we have it down here, we want it up top. We notice that we can write 2s minus 17 in this way. Then algebraically separate it. Now notice up here we have s minus 4. Here's s minus 4. This is just cosine of t shifted by 4. Over here, we've now factored out the 9, so we have a 1 here and here. Now this is just sine of t shifted by 4. When we take the inverse Laplace transform, we get exactly as we had mentioned earlier, where we get 2 times cosine, because this is just cosine, or the Laplace transform of cosine, but it's shifted by 4, so that gives us the e to the 4t. And then same thing here with sine. Because of the shift, we get this e to the 4t, otherwise it's just sine. Now, instead of solving just a singular equation, let's try solving a system of equations using Laplace transform. Suppose we have this system here. Now what we'll do is to each equation in yellow and in cyan, we'll apply the Laplace transform to both sides. So let's do that. First with yellow, we apply Laplace transform, then we rearrange it like so. We'll call this equation 1. Then do the same thing with cyan, where we've applied Laplace transform to both sides of this right here, and then rearrange it to get equation 2. The first step of applying Laplace transform to a system is to get a system of equations, namely equation 1 and equation 2. And from there, we're going to solve individually for L of x and L of y. So we've done our first step. Next, what we'll do is isolate each of L of x and L of y. Since we're trying to isolate each of L of x and L of y, what we want to do is eliminate one of them to start with. Let's try eliminating L of x so that we can isolate L of y. We start by multiplying the gold equation by c. Every term is multiplied by c. And you will, no pun intended, see why we're doing this. We also take cyan and multiply everything by s minus a. The reason being is now if we add these two equations, we can see that the first two terms will cancel. After adding them up, we get negative bc plus this here times L of y, and then we get this over here. From here, we isolate L of y further to end up with this expression. And now if we wanted to change notation, we might write capital Y of s or L of y, just a relabeling. But this would isolate L of y. We would do exactly the same thing to get L of x. Then, at that point, to find y, we know we just have to take the inverse Laplace transform. Let's go ahead and walk through an example where we have specific values, and we'll see how this all works. Say we have this system. We go ahead and apply the Laplace transform to both sides of the yellow equation. And if we rewrite it, we can get an equation 1. Do the same thing with the cyan equation. This gives us an equation 2. We now have our system. At this point, we want to isolate L of x and L of y. We'll start by multiplying the first equation by 3, the second equation by s minus 3, so that when we add them, we isolate L of y, just as we saw in the last few slides. Then do a little bit of algebra further, do some algebraic simplification. At this point, we can factor the denominator. It factors like so. That means that we can go ahead and apply partial fraction decomposition, since this is just a product of two linear factors. Then from there, we'll take the inverse Laplace transform, giving us this here. Now the a and b can be found algebraically, and we've done this numerous times, so I'll skip that for now. And if we wanted to find L of x, we would go through exactly the same process. Once we took the inverse Laplace transform, that would give us x of t. I hope you found this video useful. We'll see you in the next video. To view the next video in this series, click the link on the right. To view the last video in this series, click the link on the left. If you want to learn more about me, the nerd who's making these videos, visit the website below. And as always, have a good day.